Okay. So any questions so far? So last time we discussed a couple of examples actually regarding this Fourier transform. So you can easily evaluate the Fourier transform x omega or xj omega by integrating the time domain quantity like this. Similarly, you can get the time domain quantity by doing the same integration like this. So this is actually called this Fourier transform. So whatever the time domain quantity can be transformed into frequency domain. So this is time domain and this is frequency domain. So this t, which is the independent variable, basically represent the time domain quantity. So x, capital X within bracket omega gives the Fourier transform of xt, and here the independent variable omega represent the frequency domain. So this is the Fourier transform. So similarly, you can have this inverse Fourier transform. So in that inverse Fourier transform, you have x omega. So this is now in frequency domain. So it's converted into time domain. So this is time domain. So these are the two important equations. So this is an open book exam. So basically, so you have to go through this online evaluation. So you don't need to remember these equations. You can just get it from the lecture slides or whatever the material. So this is the summary equation which we discussed in the previous sessions. So if you want to evaluate the Fourier transform, just evaluate this integral by plugging your xt here. So it gives the Fourier transform of x, simple x. So normally we use simple letters to time domain quantities and capital letters for frequency domain quantities. So it's just a kind of a notation. So then we basically go through this first exercise, which is in the slide set. So exercise 1. So there we found that if you have this kind of time domain quantity, so this is your xt. So the value here is 1. Here we have t1 minus t1. Then this is t by 2. This is t by 2. So this is the graphical representation of xt. So we can map it to the mathematical equation. So you can define xt like this. So we have basically two values. One is 0, the other one is 1. So 1 when this t less than t1. So this mod t less than t1 means this basically say like your this. So your function is giving a value of 1 when this t is in between minus t1 and plus t1. So then 0 for otherwise case. So this is the mathematical definition of this graphical representation of xt. So again, if you want, you can put that. So it's no need to put this period. Okay, so then you are asked to evaluate the Fourier transform of this. So then we found that this Fourier transform is actually, so the Fourier transform x omega x j omega whatever. So this capital X represent the Fourier transform of the simple x equals to 2t1 sinc of omega t1. So then we found that, so this is something like, this is a kind of a sinc function, and the magnitude at omega equals 0 is 2t1, and these are like, so you can easily value these crossing points. So how do you get the crossing points? So the inner argument wt1 should be a kind of this. It's a kind of a multiplication of files. So then you can come up with this kind of n phi over t1. So n is a kind of an integer. So we can simply substitute different n values and find this. So here actually it's like phi over t1. This is 2 phi over t1. This is minus phi over t1. This is minus 2 phi over t. So see, like here, so we have time domain. Here we have frequency. So this is a time domain quantity, and this becomes a frequency domain. So this is the Fourier transform of xt. So then we explain like, so how, if it is a kind of a periodic sequence, if it is a periodic signal which is actually generated or developed from this original xt. So if this is a kind of a periodic function which is derived from xt, so you can simply obtain the Fourier series coefficients by looking at this x omega. So there you can, we found that Fourier series coefficients can be obtained like this. So here the period is t, equals to 5 omega naught. So if this x tilde t is a kind of a periodic function which is simply derived from xt, so keep in mind it should be derived from xt. So if it is something else, so you have to be more careful. So either you cannot directly write the Fourier series coefficients, or you need to apply kind of a properties of this Fourier series called Fourier transform. For example, so let's think about this kind of a pattern. So now we have like x1t. So by looking at this x1t, so we know that it's a kind of a shifted version of x tilde t. So then you cannot directly write the Fourier series coefficients of x1t. So you need to build a relationship between x1t and x tilde t. So you know that, so we can write the Fourier series coefficients of x1t by plugging a kind of a exponential component which is mapped to this shift. So this is basically shifted by t1. So you can add a kind of a e to the power j omega naught t1 component. So then these Fourier series coefficients are basically multiplication of the coefficients of this one into e to the power j component. So then you can write the Fourier series coefficients of x tilde t by looking at this x t Fourier transform. So that's why I specifically mentioned that for some cases, so you cannot directly write the Fourier series coefficient, but you, in addition to that, so you have to apply Fourier series properties as well. So this is the stuff we discussed last time. So hope you went through the video. So then we'll move to another example. So this exercise 2, we basically discuss about this. So then xt is a kind of a function like this, e to the power minus at xt, where a is greater than 0. So we found that the Fourier transform of this time domain quantity is something like that, 1 over a plus j omega. So this is a kind of a complex quantity. Because here you have j component here. So a is the exponent and omega represent the frequency domain. So this basically represent the frequency domain. So this is the Fourier transform of this e to the power minus at ut. So by looking at this xj omega, you can simply say that it's a kind of a complex function. So if it is a complex function, we know that we can simply derive these two quantities. So this is the magnitude spectrum. So this is the phase spectrum. So we found that magnitude spectrum is simply this. And the phase spectrum is like minus tan inverse omega divided by a. So then we plot these two quantities, magnitude spectrum and phase spectrum. So it's given in the slides. So then we move to another example. So this is exercise 3. So now your function xt something like that. Okay. So instead of this t, so we have mod t. So then how do you find the Fourier transform? Fourier transform of xt. So you just put the definition here. It's minus infinity to plus infinity xt e to the power minus j over t dt. So we know that, so this xt, so if we consider the range of this t, so this basically the t is actually from minus infinity to plus infinity. So during this minus infinity to 0 range, so this t is a kind of a negative value. So from 0 to plus infinity, t would be kind of a positive value. So then we can split this integral into two, from minus infinity to 0. So you have xt here. Now xt becomes, because now t value is minus, so you have at e to the power minus j omega t dt, plus from 0 to plus infinity. So this t is positive, so your function would be e to the power minus at. So then j omega t dt. So if you solve these two integrals, we will end up with 2a divided by a squared plus omega squared. So this is the Fourier transform of xt. So by looking at this, you can simply say that this is a kind of a real function. So then you don't need to worry to convert it to magnitude and phase, because we know that if it is a real function, this magnitude would be the same and the phase would be either 0 or 360 or 25. So this is the magnitude. So you can just plot the magnitude spectrum. So here it is equals to exactly similar to this, because it's a real function. Okay. So if you have any questions, so if not, we'll move to the exercise 4. So this is EX4. So I'm referring the slide set uploaded in the Sims. So hope you have these presentations. So in exercise number 4, so we are focusing on inverse Fourier transform. So the inverse Fourier transform is a simple xt. Okay. So this is the fundamental equation. So you are given that the Fourier transform is this 1, 0. So the frequency should be in between capital W, and this is otherwise. So if you plot this, it's something like this. So this is xj omega, here, yes. Here the value is 1. So previously we discussed a kind of pulse in time domain. Now in this case, so we are given a pulse in frequency domain. See that? So this is in frequency domain. Okay. So this is Fourier transform of a kind of function xt. So this is actually a Fourier transform of a kind of a function xt. Now you are asked to evaluate this simple xt, which is a time domain quantity. So you just plug it to here. Xt equals 1/2 So the integral. So minus infinity to plus infinity. So we know that this function is defined only between plus minus and plus w and minus w. So this integral is simplifies to this plus w to minus w x omega. So during this period, so the x omega would be 1 e to the power j omega t. Okay. So this is actually, you will end up with this kind of a function. So this is integrate with respect to omega. So you can treat jt as a constant minus w plus w. So this is equals to, so e to the power j omega w minus e to the power minus j omega w, sorry, tw. So this is different, integrate with respect to t. So this is jtw divided by jt. So then this is equals to sine. So if you put 2 here, 2 here, and 2 here. Sorry, so there's a 2 5 there. So we have 2 5 here. So then we can treat this quantity as a sine function, sine w t, so divide by phi t. So then we can further simplify this by converting the sine function to sin function. So sine wt, so you need to put w here and phi t is already there, so you can put w to cancel this out. So then this becomes w over phi sin wt. So this is the, so if you draw the spectrum, so this is now in time domain, so it's a sin function. So here the value is w divided by phi, and these are actually, so you can easily get these two set of values. W t would be n phi. Then t would be n phi divided by w. So the first value is actually phi over w. So this is 2 phi over w. So this is minus phi over w. This is minus 2 phi over w. So this is actually xt. So you have a function like this. In time domain. So you will ended up with a kind of a function in, sorry, frequency domain, and once you apply inverse Fourier transform, you can convert it to a kind of a time domain function like this. See, so here we have 1, here we have w over 5, here we have w, here we have multiplications of W over 5. Okay. So this is just for the clarity. So keep in mind, like, so we have a kind of a rectangular pulse in frequency domain. So if you have a rectangular pulse in frequency domain, so the time domain representation would be time domain. It's a kind of a sinc function. So if you have a kind of a pulse, rectangular pulse in frequency domain, so you can map that into a kind of a sinc function in time domain. So this is actually, so by looking at this, it's a kind of a filtering arrangement. So in between minus W and plus W, so this basically filter the whatever the input signal, because the domain outside this W's, the functional value is 0. So then it means whatever the frequency component are simply suppressed to 0. So if you multiply this input signal, which is in frequency domain, with this filter, so let's think about this kind of thing, x j omega into x omega I. So this is your input. So if you multiply this, so during this block, so the x j omega would be 0. So then it means like whatever the frequency component outside the spectrum is simply suppressed to 0, and it's just past the component, frequency component in between minus W and plus W. So this is kind of a filter. Filter response in frequency domain. So this is a filter response in frequency domain. So it's a kind of a, so you can assume that this is a kind of a low pass filter. So whatever the frequency component between 0 and W are simply passed. So we can basically assume that the bandwidth is 2 times W. So the bandwidth is 2 times W, and whatever the frequency component in between this minus W and plus W simply pass to the output side, because the magnitude in between these two frequency block is +1. So there won't be any gain, but it's just pass the input to the output side. So this is 1. So you can, this is x omega out. So your x omega out would be simply x in when this frequencies are in between the minus W and plus W. If it is the other way, so this x would be 0 and you don't see any x output. So this is a kind of a low pass filter. So now we can simply say that, so this is the filter response or the low pass filter response in frequency domain. So this is the corresponding response in time domain. It's a kind of a sinc function. It's a kind of a sinc function. So from this we can have kind of a small conclusion. So for the low pass filters, frequency response or the frequency domain representation is kind of a triangular function in frequency domain. So once you convert it to the time domain, it's a kind of a sinc function. So this is the relation. So this is low pass filter. So similarly, you can get the high pass filters, band pass filters, anything. So by shifting this original signal, so then definitely the sinc function also shifted by certain amount. So we'll discuss it later. Okay, at the same time, so C, What happens if we change this W? So what happens if we change this W? So now we know that so here we have W minus W, here we have 1. So this is actually X omega. So I'll drop this omega for the time being. So if it is a kind of a time domain quantity, it's something like that. So this would be W05, and this is phi over W. This is 0, this is minus phi over. So what happens if we change this? If we increase W, if we increase W, so it means like it's something like that. So what happens to the spectrum or the time domain quantity? So if we increase this W, so this magnitude would be increased. So then you have this, you have a high peak here. So this is the W05. So once you increase W, so the amplitude at t equals 0 is simply increasing. So what happens to this quantity? Phi over W, once you increase W, this phi over W becomes small. So then you have this kind of a signal. So this space is actually 2W05, 2 phi over W. So this is W05. So this becomes increase and this becomes decrease. So it means if you consider a wideband scenario, if you consider a wideband signal, so you will get a kind of a narrow t-domain signal with a high peak value. So if it is the other way, like if you have a narrow band signal, so then what happens actually, so this W would be small, so then the magnitude will be decreasing and the span of the main lobe is increasing. So this is increasing and the magnitude is decreasing. So for the narrow band case. So if it is a narrow band signal, so you have a kind of a time domain signal with a big span in the main lobe and relatively low amplitude. Okay. So this is the impact of wideband and narrowband signal. So if we have kind of a wideband low pass filter, so this would be the response. So if it is a wideband low pass filter. if it is a narrow band low pass filter. So so later on you can think of what's the real impact of this one. So this is actually leading to kind of like if you want to sample the signal, so there's a huge impact of this one. So what happens if you are dealing with narrow band, what would be the sampling, and if it is a wide band signal, what would be the sampling. So this is a link with the sampling, so we'll discuss it later on. So for the time being, keep in mind, if it is a wide band signal, your time domain spectrum would be very narrow and the amplitudes are getting higher and higher. If it is a narrow band signal, so your time domain signal is a kind of a sinc function having a reasonably high span for the main lobe, and the amplitude of this main lobe is decreasing. So next thing is a kind of so this is called duality property. So duality property actually discuss a kind of a relationship between time domain and frequency domain. So this basically explain this, like for example, we have a kind of a time domain signal giving a, so this is the Fourier transform. So we have a time domain xt, simple xt. So once you apply Fourier transform, we'll get a kind of a capital Xj omega, which is now in frequency domain. So this is your independent variable in time domain. This is the independent variable in frequency. So keep in mind, now this is in time domain. By applying Fourier transform, we'll convert it to the frequency domain. So what happens if we have kind of function in time domain? So this x represents the pattern of this function or the shape of this function. So this capital X represents the shape of the function in frequency domain. So this for the time being, let's assume that. So this x actually represent the shape of the function in time domain. Capital X represent the shape of the function in frequency domain. So this is the shape of the functions. So these are basically shape of the function. This and this represent the independent variable in time and frequency domain. So now we have a kind of a function in time domain which is exactly same as x. So it is exactly same as this function, the shape of the function. So once you apply Fourier transform, you will get a kind of a, okay. For the time being, let's assume like this. So we have this kind of a time domain function, xt. So let's assume if we apply Fourier transform, and we'll get this kind of a function in frequency domain. So this duality property itself gives a kind of indication about if we have a time domain function like this, very similar to this capital X. So if you have a time domain function like this, if you have a time domain function like this, so the shape is same. Shape of the functions are same. Because x itself represents the shape of the function. So the shape is preserved, and we change the frequency domain variable with time domain quantity. So in that case, so we have kind of a similar function. So we have kind of a x minus j omega. So we know that if we have this minus j omega, it means like we have x omega, or this function is mirrored. So this t is simply mirrored. So you just scale it by 2, 5, and xt is mirrored, and replace t with omega. Okay. So if you have, so we basically do this. So if you have function xt, if you have function xt in time domain, and if you know the Fourier transform of this xt, which is x, capital X j omega. So if you are given a function which has the similar shape of x in time domain, so you can easily obtain the frequency domain response of this by just scale this xt by 2, 5 and take the mirror image over the y-axis and substitute omega instead of t. Okay, so this is already proved. Like for example, if we refer the previous set of examples, initially we discussed this kind of example. So we apply Fourier transform and we obtain omega t1. So later on we discuss this kind of signal. So then we discuss this. And once you apply inverse Fourier transform, we obtain this kind of person. So let's, so we, very first example, we have kind of a rectangle pulse in time domain. So then we apply Fourier transform and found that the Fourier transform of this x j omega is a kind of a sinc function having this amplitude, and the pattern would be omega t. So this is the pattern. So then just before these couple of slides, we discussed the inverse Fourier transform. So we discussed one example for this inverse Fourier transform. So there we consider a kind of a signaling frequency domain, which is a kind of a rectangular pulse with a magnitude of 1. So we explained that this is a kind of a low pass filter response. So then we apply inverse Fourier transform and obtain this kind of a sinc function which is in time domain. So this is in frequency domain, this is in time domain. So now this is in frequency domain. So this is in time domain. This is frequency domain. So this is frequency domain, this is time domain. Now just compare these two. So just compare these two. So this is a sinc function and this is a sinc function. But there's a different scaling here. Okay, let's assume for the time being we have 2t1 here also. So let's assume this is actually 2t1. Okay. So we have function. So this is frequency domain function. So this is 2t1 sinc omega t1. And there's a function in time domain. Let's assume that the magnitudes are same. Sinc wt. So this is the frequency domain function. This is time domain function. You see that? So the pattern is very similar. So they exactly same. So this pattern here 2t1 sinc omega t1. Here you have 2t1 sinc omega t. Here this is the variable in frequency domain. This is the variable in time domain. So what we can simply do is, if this is the function we need to find the Fourier transform. Let's assume. So we need to find the Fourier transform of this. So need to find the Fourier transform. So using duality property, we can simply say that the Fourier transform of this is, so you just multiply this with 2 5, because we know that this Fourier transform is come from this time domain quantity. So then, so the Fourier transform of this would be a kind of a function. So we need to take the mirror of this one. So once you take the mirror, if it is a rectangular function, so the values doesn't change. And the magnitude here is now, we know that this, so we need to scale it up with 2 5. So then this becomes 2 5. And these values, what about this one? In time domain, those are t1 and minus t1. So by looking at this one, see that capital omega is equals to t1. So if this mapping is work, so this t1 is equals to capital W. So these functions are exactly same. If this t1 is equals to capital W, so these two quantities are exactly same. So this is in frequency domain, this is in frequency domain, and the shape is preserved as it is, and this is now in time domain. Once this t1 is exactly equals to W, so we can simply say that these two functions, one is in frequency domain, the other one is in time domain, they are exactly same. So if they are exactly same, the function in frequency domain and function in time domain, if they are exactly same in the shape, so you can easily get the Fourier transform of this time domain quantity by looking at the transform of this this. So then we can simply say that here it would be W and this would be minus W. So we know that T1 is equals to W to match these two together. So we can easily say that this is W. So you just replace T1 with capital W. So this is minus T1 with minus W. So then this is the Fourier transform of this time domain quantity. But we found that this is like with a different scale. So W over 5. So let's think, like if this quantity makes to 1, it means like if we multiply this 2 5 with omega of 5, what happens? So this 5 to 5 cancels out, we have 2W. So 2W equals 2T1. So if this is mapped to 1, so then ideally this scale would be W over 5. If it is 2T1, so this scale would be 2, 5. So what I want to highlight here is we have a kind of a function xt and a Fourier transform of x omega. Actually, we have a time domain function. Keep in mind, if you have a time domain function exactly matching with the shape of this frequency domain. See? So these are exactly matching shape. So then you can easily evaluate the Fourier transform by scale up by 2 pi and take this function and take the mirror image first and substitute t with omega. So the here scale up with 2 pi, take mirror of xt, replace t with omega. So nothing else. So we take this time domain function and scale it up to 2 pi, then take the mirror image and replace t with omega. So this is very simple. So we'll take one more example for this one to make it clear. So we know that, so we had a one example like this. So you have xt which is equals to e to the power minus at ut. So we found that xj omega equals 1 over a plus j omega. Okay. So let's assume, so we have yt, so yeah, yt which is equals to 1 over a plus jt. What would be the Fourier transform? Yt. So if you compare these two together, so we found that, so this is the Fourier transform of, so this is the Fourier transform of xj. So we have time domain quantity and the shape of this time domain quantity exactly matches with xj. So the shape of yt equals xj omega. So see, like if you replace omega with t, so you have this. Okay. So then we know that how do you get the frequency domain or the Fourier transform of this? So it's actually, so we have to take this xt first. So I have to take xt first. So we'll take xt. So then we'll multiply with 2 phi. So then we have 2 phi xt. So then take mirror. So then 2 phi x minus t. So then sub the variable or replace t with omega. So 2 phi x minus. So we'll do the same. We'll take xt, multiply with 2 phi. So this now xt is actually to the power minus at ut, multiply with 2 phi to the power minus at ut. So then take the mirror. So then 2 phi e to the power at u minus t. So then sub t with the omega. So then you have 2 phi e to the power a omega u minus 1. So this is the Fourier transform of, actually this is the Fourier transform of 1 over a plus j. So first we'll take the xt, then multiply with 2 phi. So now it's become 2 phi xt. So then take the mirror. So then this xt becomes x minus t. So this is the mirror. So then replace this t with omega. So you will get this. So we'll apply to here. Take this. This is your xt. So then multiply with 2 phi. So it will become 2 phi to the power minus 8 ut. So then take the mirror. So then this t becomes minus t. Oh, this is like that. So we have this kind of a function. So once it's mirror, so it's something like that. So let's take the mirror of this. So then the function is simply negative. So negative means, so we can simply say that this is negative. See, u minus t is a mirror of ut. So this is your ut. So this is the unit step. 0, this is 1, this is ut. U minus t, something like that. 0. So here it's t. This is 1. This is u minus t. So this is 1 from minus infinity to 0. This is 1 from 0 to plus infinity. Ut u minus t. So it's very simple. So this is a mirror of that one. So then replace this t by omega. So you have 2 phi for a omega u minus omega. So this is the Fourier transform of this. Okay. So hope it's clear. Okay, so let's move to the next slide. So it basically cover the Fourier transform properties. Because we know that if we want to go into the deeper and analyze the Fourier transform, so we know that. So you have to solve this. So this is the Fourier transform. So if you are not in a position to do this integration, so you can't do you cannot evaluate the Fourier transform. So by assuming that this most of you are coming from this technology background, so we basically omit this very complex integration. So we can stick into that very basic integrations. But if it is a kind of a complex integration, so this the students come from technology background may are not in a position to solve these complex integrals. But I know that, so those who came from physical science background, so they can manage it. So that's why, so we just omit these heavy integrals, and we'll try to get the Fourier transform of this most of the signals by using their properties. So rather doing or solving this hectic integral, so we can simply stick into the properties of the Fourier transform and do kind of a reasonable fair job. So the first is like, so the first property is linearity property. So the linearity property means like, if you have xt and the Fourier transform is xj omega, if you have yt and its Fourier transform is yj omega. So if you have a function like this, axt plus byt, and if you are asked to evaluate the Fourier transform, so you can treat it like two functions and apply Fourier transform separately. Like you can take a out, apply Fourier transform to xt plus b out, apply Fourier transform to yt. So we can do that. So the Fourier transform of xt, once you apply Fourier transform of the xt, so this becomes xj omega, and if you apply Fourier transform to y, it becomes yj omega. So then ideally this is a x j omega plus b y j. Okay. So if you have this kind of a linear combination of xt and yt, and the individual Fourier transform of xt and yt are x j omega and y j omega, so you can immediately get the Fourier transform of this linear relationship like this. So for example, so you have like xt minus 2xt, like 2 minus 3xt. So now this a becomes 2. So this is x1, x2. So b becomes 3, and so you can simply get this 2 times the Fourier transform of x1. If you know this, x2. So we'll discuss one or two examples later on, but for the time being, let's assume like if it is a linear combination of xt and yt like this, a and b are kind of any kind of constants. So you can easily get the Fourier transform of this linear combination. So you can take this linear combination like this. So then the second is like time shifting. So if you have function xt, just the Fourier transform this, and if I ask to evaluate xt minus t norm, so this is easily get it like this, e to the power minus j omega. So you can put this t naught here and the Fourier transform of xt. See, so you can add this exponential term in front of the Fourier transform of this original signal. So this is the original signal. So this is the time shift time shifted version. So if you want to get the Fourier transform of time shifted version, so you can easily plug this multiplication factor here. So you can put this multiplication factor, which actually comes from this delay, and just multiply it with the Fourier transform of this original signal. So for example, so if you are given xt minus 2 to evaluate Fourier transform, you can just plug e to the power minus j omega 2 into x. So if you know this Fourier transform of xt, so you can easily get any shifted version. So this is the second. So the third is actually the conjugate symmetry. So if you have a function like so if you have a function xt, and if you are asked to find the conjugate of xt, so this is actually x conjugate minus j omega. So you take this Fourier transform x j omega, then take the mirror, then conjugate. First take the mirror, so then once you take the mirror, it becomes x j omega. So if you take the conjugate, it becomes x conjugate minus j omega. So again, like so if you have a kind of a time scaling x80, so for example x 2t, x half t, x 3 or 2t, like this. So if you introduce a kind of a time scaling here, so you can simply obtain the Fourier transform like this. Xj omega over. So keep in mind, like once you convert it to the frequency domain, you have the scaling factor here. So this is the scaling in amplitude. So this is the scaling in amplitude. Scaling in amplitude. And at the same time, so this is actually scaling in frequency domain. So keep in mind, once you introduce a kind of a scaling factor to time, so this scaling affects to the amplitude as well as the frequency. See, so this amplitude, so it's affect like this, and frequency it's affects like this. So keep in mind, if you introduce a kind of a scaling to the time domain, it affects both to the amplitude of the spectrum and the frequency scaling. Like so, this A introduce a kind of expansion or compression. This A. So this A introduce a kind of magnification or kind of a kind of a gain or loss. So this magnitude may be increased or this magnitude may be decreased. So this spectrum would be expand or this spectrum would be compressed. Initial spectrum would be compressed or expand depending on the value you take. Okay. At the same time, the magnitude of the initial spectrum would be increased or decreased depending on the value of A. So these are the very simple set of properties. So there are a lot of properties in this Fourier transform, but we'll limit it to certain very important set of properties. So we have properties related to differentiation, integration, a lot more. But we'll stick into this very simple set of properties because so we can deal it easily. So once you go for the these other properties, you need this integrals, differentiations pretty much frequently. So that's why we stick into this simple set of properties. So we can do a kind of a good job using these properties. So we'll stick into this simple properties and we'll try to solve or try to get the Fourier transform of couple of signals. So we'll do it in the okay. So we'll move to the last example in the same slide. Okay. So we'll do. So I'm referring this exercise 6, EX6 in the slides. So you are given a kind of a signal like this. So this is the time domain, this is 4, this is 3, this is 2, this is 1, this is 0. And here it's 1, this is 1.5. So this is your xt. Okay. So you are given a kind of a, so initially you are asked to evaluate the Fourier transform of this. Okay. So this is your Fourier transform. So we obtain the Fourier transform of this one as like 2t1 sinc omega t. So this is the Fourier transform of this. Now you are asked to find the Fourier transform of this. So by looking at this, you can find this shape. So we can easily identify two blocks. So one is something like this. So the other one is something like this. Okay. Once we just add these two together, so we can have this original function. So let's assume this is x1t and this is x2t. So we know that by looking at this or x1t, so like so by looking at this one, we can simply say that so for this is actually so they here the center is somewhere in this. 2.5. So then this is actually shifted to 2.5. and t1 goes to, so in this case t1 is actually 1.5. So we can obtain this function by substituting t1 to 1.5 and shift this original version by 2.5. Okay, so it means like this becomes like 2t1, so it's like 3 times sinc omega t1 becomes 1.5. So this is simply shifted by 2.5, means you can easily introduce a kind of a prefactor here, which is actually j omega 5/2. So just replace t with 1.5 and then it becomes like this. It's 1.5, it's minus 1.5, this is 0, and this one. So then if you add a time shift, so then this becomes like this. So this moves to 2.5. So then this is 2.5. So this is actually 4. This is actually 1. This is 0. So this shift, you can accommodate it using this e to the power quantity. Okay. So then similarly you can apply to here as well. So in this case, you can substitute t1 as 0.5 and again add the same shift of 2.5. So then initially it would be like this, 0.5 minus 0.5. So then add the shift, it moves to somewhere like, so it's 2.5, this is like 3, this is 2. So then for this case, so the same shift, e to the power j omega 5/2. So then t1 becomes half. So then you have 1 here, sinc omega over 2. Here it's omega over, here 3 omega over 2, here omega over 2. So then if you sum these two, so you can take this e to the power factor out because it's common, j omega 5/2. So then we have 3 sine sinc 3 omega over 2 plus sinc omega over 2. So this is the Fourier transform of this given function. So we basically use two properties. First property is actually, so we use one property, so it's like time shift. Then the second one is linearity. So likewise, we can discuss a couple of more examples to make it clear. So we will do it next time. So I upload a couple slides which we basically discuss 6 examples where we can apply this Fourier transform and inverse Fourier transform in different ways. So just go through this one and we'll discuss it in the next time. Okay, so do you have any questions so far? So if you don't have any questions, so we'll wind up the session for today. and I'll upload this video to the Sims. If you have any questions, just drop an email or just drop a kind of uh, you can share through the discussion. Okay then. Okay. Thank you.
Thank you, sir.